administrative notes, and I probably try to quickly derive, or maybe even invite you to derive a couple of equations, and then quickly go through slides where they show it. So the goal is to travel from T D SE to T I SE. Can you guess what are they?
Time, distance, no.
Time is good.
Time.
This place is 132.
Just 130.
Oh, time. Wait, what did I hear? Like distance or displacement?
Okay, let's skip D. What is?
Time independent.
Yeah, perfect. I knew you know this subject better than graduate students. Okay, and it will be one derivation, and another derivation will be to plane what?
Plane coordinates. Plane coordinates.
Right. Try another plane.
Plane.
Equation.
Plane.
What are we doing in this class?
Conversation.
Plane.
Trivia. Jeopardy.
What
Crash.
electrons hold properties of?
Charge.
Wave.
Yes, plane wave.
Happiness.
Wait. Pure. If it will be pure, the second word will be pleasure. Okay, so time Schrödinger equation, time dependent, time independent, and when we, I think last time we derived that if we need time derivative of the wave function, it will be the Hamiltonian operator acting on the same wave function, right? And we derived it based from the evolution operator. Now, the problem that there are two independent coordinates is a problem for differential equations. The differential equations one subject is missing this functions of more than one variable intentionally because it is a challenge. So anytime it is possible when a mathematician wants to have function of a single variable because it will be much simpler. So let's assume that this function of two variables can be represented as well, x capital of x lowercase times t capital of lowercase, or maybe some different, but as a product of two functions, each of which depend on its own variable. This is not always possible, but luckily here it is possible if the differential operators are additive. Now, if this trick is available, we want to plug this one in. Now, a week ago, I was asking you to impress me by solving a differential equation of this form. And you gave the answer. Yes, and it was, and it was like the derivative of a function equals to function itself.
Oh,
Yes, e to the power of something, like constant times t, right? So math is created by humans for humans, not as a way to torture young minds, right? Well, we get this impression in the college. I got it too. It's normal, but later on in the, so to say, adult life, you see that math is created to help us, not to create problems. Okay, so if the first derivative is expected to give solution like this, why don't we assume that this t of t should look like e to the power ct? And then, well, we can try to prove that it is wrong, and we will fail. It is indeed this way. But then the question is, we have two more questions. Well, we have many questions, but right now, active questions. What is the value of this constant? Can we find it? And what is the function for this x of x? And why are we formulating this equation? Are we going to torture each other by solving equation? Unfortunately, no. We will try to use MATLAB as much as possible for solving. I will do a couple of homeworks, well, not couple, about 10 to scare you, but finally you'll believe that MATLAB is good, equations are bad.
Okay, so if you have those like to the like x capital of x times capital T of little t, could you make like, is that a separable equation and then you could derive the time independent equation from that?
Exactly. So you're ready to deliver today's lecture just from the top of your head.
But doesn't it have to be e to the power of t plus a constant? Because if it's e to the ct, the derivative
Please dictate me. I'm not as good in listening. Okay. E to the what?
e to plus c. Because if it's e to the power of c times t, the derivative is c e to the ct, so it's not the same.
Yes. Well, let's put C here to
That works.
okay. Right now we are worried about functional form, right? But thank you. I see you are either very intelligent or very knowledgeable, or both.
I'll put a half to.
Okay. So why do we need this equation, and how does it help chemistry?
I had no idea.
Come on. I've told it at our first meeting. So if anyone asks,
When I have breakfast. That was about an hour.
yes, predicting the future of chemical reactions. So if you have reaction coordinates, right, there is a probability distribution, and we look for probability to overcome the barrier, right? And this is the function. The barrier is here in Hamiltonian, and as we go through time, we go from reactant to product. Okay, so it is a motivation. Motivation.
I'll speak for surrender.
Okay, I do not know which one to use.
Wow.
It's a big doubt. Or the same rank as remembering meal for breakfast. Okay, so just plug it in. So d dt x e c t minus I h bar h x e c t. So here we have time. If you want to be meticulous, it is derivative of first times second unchanged plus first unchanged times derivative of second, right? And x, by our assumption, it is not time dependent, so we drop this, right? And here, as Elsa noticed, the power goes up front. This like c x, and then derivative of exponential is exponential itself, right?
Yes.
Okay, and on the right, what do we have? So the Hamiltonian is time independent. It doesn't have neither derivatives or explicit time in most of the problems, so it will not affect the.
So you can divide out the e to the ct on both sides and it'll cancel, right?
Exactly. So
What just happened?
This is how we make the time independent equation.
Oh,
Because you see the e to the ct is on both sides because you substituted in.
Oh, and that's the part that's dependent on time, times t, right?
That is my.
As soon as we cancel this two things, all time dependence is gone.
Right.
Yeah, so
But when
so
it's-
the top one is time dependent.
Yes, and this one becomes time independent.
Okay.
Okay,
Wow.
and then we can just rewrite it nicely. So, I'm also not happy with uppercase X. Let's use phi, and I'm in doubt which to use. You see in notes, I'm jumping with.
Just use delta instead.
No, I'm against it. No, delta is too small.
Delta is a good Greek letter.
Okay, so C phi of X equals minus I h bar h phi of X.
Wow.
That's a good one.
So this is differential operator. This is unknown function, and I'm just a little bit unhappy how to interpret what is C.
It is a number.
But is it real or imaginary?
Oh,
Is it positive or negative?
either.
What is physical meaning or chemical meaning of C? So we can
C is.
minus HA times C phi equals H phi, right?
Sure.
And then what is H?
Hamiltonian.
And Hamiltonian has a dimension of?
I have no idea.
You do.
Is it 3D? What? Dimension?
Like time, units.
Oh, you got me here, Dimitri. My man. I don't know. All right, let's talk it through. That's how we tend to do very well in this class, am I right? As you all know,
So any suggestions? Where did we get it? So suppose I haven't read any single book. I just watched what we talked here. Yeah, it's too hot. Maybe in the other room will be a little better. So where did we got it? We were putting evolution operator minus I integral Lagrangian dt, and Lagrangian is like t minus u, or later on we change it, and t and u are kinetic and potential. What? He was right, but it's
Energy.
yes.
I was yawning.
So H
Is energy.
units of H is energy.
So that's
Then
real.
then units of this thing is also energy, right?
Okay.
Energy.
So then your C is gonna be a real
So
number.
E
That can be positive or negative.
equals minus H over I C. So I E divided by H bar is minus will be C. So energy is real, right?
Sure.
I is imaginary. Real times imaginary will be imaginary. So C has meaning of energy, but it is imaginary.
Don't the I's cancel out?
Or
No, I'm saying,
is there is only one I. How to cancel?
but if you plug that in for C,
Mm-hmm.
you get the I's on the left side cancel. The H bar cancels, you get.
What are you plugging in for C?
Or
what he
you
has on the board.
or you want to scroll the derivation back, and then you'll get C equals C,
Yes.
which is absolutely correct.
I see. The,
Yeah, it's just
I
an
see through the
arrangement of
line
the-
and P.
So T of T is e to the power minus I over H bar energy times T.
It's imaginary.
Okay,
Just like all of my hopes and
does it look similar to this one?
yes.
But here it is something that depends on also position on trajectory, right? And here is depends only on time. So if you know the energy of an electron, of quantum state of an electron, with time it will accumulate phase. It will just imaginary phase. Okay. Okay, and where is our time independent Schrödinger equation? So H phi equals E phi. Agree? So the goal of the course in the narrow sense is just to solve this equation for different quantum systems. Like if, well, I wish and I hope you all will go into research and academia and industry, but maybe by some reason you need to teach, or maybe you, when go into graduate school, you need to teach the same class or wherever outreach in four-year college. So in simplified versions of the quantum theory, one shrinks it to maybe 3 meetings. First meeting, declaring this equation. Second meeting, applying it to the square box where electron is enclosed. And third meeting, quantizing nuclear degrees of freedom for harmonic oscillator. And then you tell, hello guys, you are experts in quantum theory, go to the next subject. We'll go a little bit deeper, but this is one of the cornerstone which you cannot skip even if you want to make it really, really short. Okay.
So we've got the first objective done for the day.
Yes.
Perfect.
Can I take a picture of the board before
Oh,
you?
yes, please. Yes, please. You can even send it to me.
That's
just.
Or maybe it's sent to the whole class. Yeah, good.
Yeah, let's just all.
okay. I'm good.
Thank you. It's with a modern technology, one can, like in old times, it was supposed that everyone takes notes, but now one can either not take in notes and looking into the electronic notes, or assign one person on duty. Each time it will be different one.
Yes, and you're not.
Okay. Looks like I'll just disappoint.
So who does, oh, Melody, you are doing number 2 on Friday.
Sam's doing number 2.
I need to swap them. Okay. For Sam. It's a hard well, number 2 is a hard subject.
Hey. So what you're saying is like, if I impress you, I'm in.
Yeah.
I'm solid for this. That's good.
So whoever does number 2
Yep.
needs to explain what is inside this energy operator.
All right, so I'm dropping this class.
And
As long as you start at 11 o'clock at night, they're gonna be.
I'll be starting it at some point. Now.
What about that?
What's in it?
what is inside? What is in it?
Melody, you want
So so this H is we can tell that it is kinetic energy, kinetic plus potential.
Oh.
But what is an equation for kinetic energy?
Bro, I looked everything up in my physics class. I have no idea.
Yeah. Negative 1/2
MV squared.
mv squared. I disagree with minus.
Oh,
I would go for plus. The higher the energy, the higher velocity, the higher the energy. Right? Negative energy, it means too attractive. Negative is like,
I think that was.
well,
Oh,
okay. And potential
Is
is much bigger problem because it changes every time. Right? But by the way, we'll talk about potential later. Velocity and mass are not universal. It's a little better to replace mv as p, okay, and then it will be p squared over 2m.
okay.
Right?
Yeah.
Momentum.
So P equals P
If look here, we like mv but in the denominator, we need to add another m that we can cancel frivolously or keep it here. Okay. And then what I'm going to, we have less and less time, but I will try to squeeze first by speaking and second by showing slides, maybe in the last 5 minutes. There is a very big challenge, surprise, intellectual shock, unexpected thing, which later will become like an alphabet of quantum theory, but right now we need to overcome it. And the P expressed in terms of classical theory, which is just a variable, in quantum theory is differential operator. And this differential operator is proportional to the derivative over space.
That's supposed to be like,
Well, it is my perfect calligraphy.
it's pretty well
Yeah.
spelled. I had no idea.
I was reading a joke yesterday. I have only, well, I'm not telling about myself. It is from the character. I have only one weakness. I have an exaggerated self-esteem. In everything else, I'm perfect. Okay, so Hamiltonian is composed of differential operators like this. And practical way to use quantum theory is to identify how to populate Hamiltonian with differential operators and then solve this differential equation. Basically, the postulate number 2 summarizes this idea and gives examples of the differential equations for different variables. And in the remaining, whatever, 15 minutes, I am going to make this idea a little bit less shocking, a little bit more pleasant for all of us. Okay, so I'm going to erase everything with your permission.
No.
I took a picture of, I have to have the like.
Okay.
Now I'm ready.
Okay, thank you.
Oh. Good thing that it wasn't calculated, if there's even anyone in.
Maybe he actually did not think when he out.
Okay, now suppose we have a solution of time-independent Schrödinger equation. Just solving equations is always a challenge. Suppose we have just like in a sandbox an equation that maybe is a solution of some equation, and just let's dissect it as kids play with toys by breaking it on pieces. So just as an example, let's look at the EIPX over H bar. Why do I select this toy to play with? When we were looking onto Bohr's model, we were telling that angular momentum is R times P. And if you take, yes. If we skip the direction, if you just, and they are orthogonal R and P, the dimensionality is the same as for action and is the same as for Planck's constant. You remember this? And you play with Bohr's model every day, and it is something that you recall again and again. It was taught to us in high school, then we forgot. It was taught to us in freshman, then we forgot. And now we remember that we heard about it.
I actually don't think we've ever had a board model mentioned by Rogers. Freshman year.
Take it once again.
No.
I think he would
Pass.
say that's incorrect.
It is incorrect, but it is a very important logical step. Without it, going directly into correct equations is too much of intellectual shock.
No, I think what she means is that my statement.
I think I feel like we did hear it.
Yeah.
I don't remember. In my high school chemistry class, but it's more likely that I was here.
No, I never heard it in high school. I don't think he ever mentioned it.
I think he did.
Okay, I'm watching another instructor teaching freshman chemistry, even for non-majors, and it is a substantial part of the lectures. So it may differ from instructor to instructor. So, Bohr's model. Distance times momentum have units of action and Planck constant, right?
Yeah.
Yes. So distance times momentum divided by Planck constant will be dimensionless, right? Dimensionless.
Because you're.
Like if distance divided by distance will be dimensionless.
Oh, you know us, sure.
Like ratio of this of the same.
Yeah.
Okay, and then since this Planck constant includes also like hidden 2 pi, the argument of this thing will be like radians, and then we remember that it is a cosine of this px over h bar plus I sine px over h bar by this I here, yes, Euler's equation. Yes, so exponential is imaginary power can be expressed as summation of real and imaginary parts.
So px over h bar is just equal to 2 pi.
Oh, same as like wrong question shows right time twice. When you travel so much distance with so much velocity, once upon a time you'll get 2 pi, 4 pi, right? So it will be periodic function, but this exponential thing is a like spiral, right? We'll get to it in one of the labs. Now, why I select this toy to play with? Remember d over something, now it's over x equals y, the solution is exponential, right? So let's check if derivative of exponential is exponential itself. Let's just make a little mathematical experiment and apply derivative over space to this trial function. So we'll get I p h bar and then the function itself, right? E I p x over h bar. So I p over h bar function itself. Do we have any take-home message? What is beautiful in here? It's oversimplified math example, and I tried to practice a reverse engineering, going opposite logic, like from solution back to the equation. But if you go typical way as we practice, you will see an interesting observation. So let me do one more manipulation and then start philosophically analyzing it. So I can multiply this one by h divided by I dx I over X, and then here it will be P of I of X. So here is a number, is actual momentum that our particle has while propagating. Here is just a differential operator, but we observe that by acting with an operator onto a function, we get a number times the same function, right? You see it, this property. Now let's look here. So we have operator acting on function, getting a number, again, the same function. So now this is eigenvalue problem. If we see operator times function equals number times function, there is a way to reconstruct the function. Here it is like trivial, oversimplified case, but as we go through the course, will be more and more realistic, practical, and interesting things. So it is about time to go to slides, and let me just announce some keywords, the terminology and context. It is very, this is eigenvalue problem, right? So the values of the numbers are called eigenvalue, eigenvalue, and the functions are called eigenfunctions, And the major difficulty and challenge and property of this type of equations that unlike 2x equals 3, right? Where one equation has one answer. This type of equations have often infinite or at least several answers. So one equation, multiple answers, multiple solutions. And this is a major challenge that we need to live with. We need to accept it. Basically, I'm done now. I'm going to summarize the same thing with quickly jumping through slides. And if you want to ask some questions, just prepare, because probably you will need to depart in 5 minutes. Yeah, so. So time-dependent Schrödinger equation. Oh, let's go back. Whoever is second, now I see it's swapped. So Sam also needs to add concept of commutation, which is here. You'll do it. I have no doubt. So here is a little new thing that I didn't mention, and it is either, I think it is postulate number 5. We will go to it again and again through the whole course, but the meaning of this equation is as follows. And it is also a very important philosophical thing, although the equation is quite simple. So this equation is a bridge from abstract theory to real life. So if you do know wave function, if you have computed wave function, and we do know a quantum operator corresponding to something that we observe on experiment, one can predict outcome of the observation by practicing this little sandwich mathematical procedure. So if you know wave function, we know the outcome of the measurement. And a little bit deeper philosophical background will be part of 3, 4, and 5. Here is what I want Sam to show in addition to his presentation, just examples of operators. And just go through a couple of them and tell what they are like. Here is what we covered. The derivative of a space is momentum, and there are a few others. So here is the last slide of today's lecture. So we need to admit that we can go from time dependent to time independent, and time independent does have multiple eigen functions and multiple eigenvalues as a solution of this equation. The property of good eigenfunctions that they are normalized. If one multiplied by itself with a star, it will be 1. If there are different, it will be 0. Yeah, I'm fine. We have more than enough time to jump through other 40 slides. Okay, so here is the little exercise that we did on the blackboard, the separation of variables, right? And if you plug in time-dependent part as exponential, we cancel this time after taking derivative, and we are arriving to time-dependent Schrödinger equation where the unknown coefficient is imaginary energy. So time-independent Schrödinger equation has multiple solutions as equations, as functions, as numbers. Eigen functions. Eigen means own, proper in German. Plane wave, if one plots real and imaginary as cosine and sine and takes it as a parametric coordinates, it will be a spiral. And this spiral is has wavelength lambda. It is called plane wave, and one can identify the distance between humps is proportional to the momentum that is here. So momentum is just 2 pi over lambda times h bar. So the plane wave is good because by taking a derivative, one reproduces it itself. And this little exercise of taking derivative of the plane wave tells us an example of eigenvalue problem. So Schrödinger equation is the not only eigenvalue problem in science and math. Here is an eigenvalue for momentum operator. By acting by momentum operator on the unknown wave function, we need to get value of momentum times unknown wave function. And if you solve this equation, the solution will be a plane wave, right? So we started in the reverse direction. Now we're going in normal direction from equation to the solution. And momentum is related to the inversely related to the wavelengths. The shape of the plane wave is kind of prompted by the units of the action and units of the position and momentum. So here is the standard way of formulating eigenvalue problem. So operator times unknown function, number unknown function, and this needs to be solved by either one of the methods. But methods of solutions are not our primary goal. Any time is possible, we'll try to just borrow solution and spend time on analyzing. And equation number 1 to be solved is time-dependent Schrödinger equation. The little index I by function and by energies stands that I labels different solutions, right? We have solution number 1, number 2, number 3, and it is a pattern that we will see again and again. Basically, we are done. We have 1 minute for questions, or you are free to disconnect from Zoom and leave from the room if you want to. Meeting is done. I look forward seeing you tonight, seeing your slides next night, and seeing your presentations